Good morning, everyone. So today I'll be talking about atomic approach to quantum technologies with giant cold Rydberg atoms. So I'll be talking about quantum technologies using exotic properties of Rydberg atoms and how it makes Rydberg atoms a promising candidates for all regimes of quantum technology. Then I'll discuss about our recent results on high sensitivity magnetometry with Rydberg atoms and observation of Rydberg excitation dynamics in cold atoms, and I'll give a future perspective on quantum information with arrays of single Rydberg atoms forming a network of fast quantum gates. So Rydberg atoms are giants of the atomic world where the outer electron is excited to a very highly excited state which imparts Rydberg atoms very exotic properties. So Rydberg atoms were discovered by Johannes Rydberg in 1888, who found an empirical formula which linked various wavelengths of the spectral lines observed in alkali atoms, and this played an important role in the birth of quantum mechanics. So what is quantum technology? So it's the acquisition, storage, transmission and processing of information using quantum sensors, processors and transmitters. So broadly, quantum technologies are divided into 4 different regimes: quantum computation, quantum sensing and metrology, quantum communication and quantum simulation. So Rydberg atoms is a versatile system which can be used for all these 4 regimes or regimes of quantum technologies. So Rydberg atoms with the electron being in a very highly excited state, it imparts exaggerated properties. For example, it has a very large size, so which makes it giant atoms which are ideal for exploring mesoscopic quantum regime, and the size goes as n to the power square. The radiative lifetime of the Rydberg atoms is quite long, which goes as n to the power cube, where n is the principal quantum number of the electronic state at which the atom is excited, and it gives long coherence time, which is very important for quantum technology applications. And the polarizability, which is the sensitivity of the atoms to external AC or DC electric fields, is extremely large, which goes as n to the power 7 of the principal quantum number, and it makes it extremely useful for quantum sensing and metrology. Also, the interatomic interaction between Rydberg atoms is very large. The dipole-dipole interaction goes as n to the power 4, and the van der Waals interaction goes as n to the power 11. So this very large interatomic interaction makes it a very strongly correlated system, and which helps in quantum entanglement via Rydberg blockade, which helps in making a fast quantum gates for quantum computation, and also it's useful for fundamental physics for quantum simulation of condensed matter systems, and also it can be used as single photon source for quantum communications. So atoms being a very robust system, because atoms are the same everywhere in the universe, so it makes it a very promising candidate for quantum technology applications, because and also cold atoms, we can access very low temperatures where we can access the quantum regime, and it has very high degree of controllability. For example, we can just switch on and off the Rydberg laser within a fraction of a microsecond to switch on and off the interaction. That means we can make very fast quantum gates. Also, we have complete control of the interatomic interaction, and the various parameters, the temperature, dimensions, spin states can be highly controlled. So the heart of the utility of Rydberg atoms for quantum technology is something called Rydberg blockade. So if you have 2 atoms which are very far away from each other, they are not interacting. But if you have one atom in the Rydberg state, and if you bring another atom closer, the energy level gets shifted because of the van der Waals interaction. And if you have one atom in the Rydberg state, the same laser, because of the energy shift, cannot excite the other atom to the Rydberg state, and vice versa. So you can see there is a correlation which is formed between the 2 atoms, which can give rise to entanglement between these atoms. So, entanglement is at the center stage, which is evident from the fact that the Nobel Prize in 2022 was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering the quantum information science. So, this is the picture of our Rydberg experiment. Shilpa, Shobhan, and Swarnabha are the PhD students, and we had Venkat as the visiting student who will be joining as PhD in Vienna Institute of Quantum Science and Technology. So, what we do for detection of this Rydberg atom? So, we use a very efficient non-destructive detection, which is the Rydberg electromagnetically induced transparency. So, electromagnetically induced transparency happens because in a 3-level system you have these 2 transitions. So, electromagnetically induced transparency happens because of the destructive quantum interference between the transition probabilities of these 2 transitions. So, you get at the resonant frequency where without the coupling beam you have absorption, but with the coupling beam, because of the destructive quantum interference, you have complete cancellation of the absorption leading to transmission in the medium. So, this is the electromagnetically induced transparency, which is our detection system. So, this is our Rydberg electromagnetically induced transparency signal, or EIT signal. So, we use this detection system to measure the transition frequencies for a very highly excited Rydberg state, because that's, as I said, the higher the excited state of the Rydberg atom, the more exotic is the property, because it goes as the principal quantum number. So, we measured the transition frequencies all the way to n equal to 125, so that we have a reference or a framework for exciting the atoms to very highly excited Rydberg states. So, these are, so we measured the transition frequency to a high accuracy of less than 2 megahertz. This is the fine structure splitting. And we could get very accurately the values of the quantum defects or the Rydberg-Ritz parameters. This quantum defects happens because the inner electronic core, so for the orbitals which are having a low angular momentum quantum number, the orbitals are penetrating into the inner electronic core. So, this makes the incomplete screening of the outer electron from the inner electronic core. So, that is the characterized by this quantum defects, which we could measure accurately. So, next we did quantum magnetometry, quantum sensing using magnetometry with Rydberg EIT. So, we put the atomic ensemble in a magnetic field using a solenoid, which is shown here, and we used an unconventional way, unconventional configuration of the probe and coupling beam. Generally, we use the probe and the coupling beam in a counter-propagating configuration, which gives us the EIT signal. But for this measurement, we also explored the other configuration where we could get the Rydberg EIT as well in the co-propagating. And to our surprise, we saw that the Rydberg EIT signal using the co-propagating configuration has much higher sensitivity to the magnetic field. So, here you can see the signal from the counter-propagating, which is the usual configuration, but here we have the signal from the co-propagating coupling beam, which has much higher sensitivity to magnetic field. So, here you can see that there are the various signal for the different magnetic field, and you can see that at higher magnetic field you have almost an order of magnitude higher sensitivity to the magnetic field. So, this makes it a very promising candidate for precision magnetometry using Rydberg atoms. So, next I go to Rydberg excitation in cold atoms. So, for the cold atoms, which we cool to 80 microkelvin temperatures, which is like a million times colder than the room temperature. So, there we use the cooling light as the probe beam, and then we use the coupling, used a 480 nanometer laser, which is the Rydberg excitation laser into the cold atoms, and we could observe Rydberg excitation signal from the cold atoms. So, here the coupling laser, which is the Rydberg laser at 480 nanometer, we are scanning it across the resonance, and we could see the signal due to the excitation to the Rydberg states. And so this is the only cold Rydberg atom experiment in India, and which opens up a lot of promising avenues for exploring quantum technology with cold Rydberg atoms. So we have two complementary detection mode. One is EM-CCD camera, where we can get the spatial information of the Rydberg cold atomic cloud, and also we have another complementary detection system which is based on avalanche photodiode, where we could get a very fast detection of the Rydberg excitation within a time scale of a few nanoseconds. So this is our signal for our measurement of the Rydberg excitation dynamics in cold atoms, where we are varying the duration of the Rydberg laser pulse, and we see we are trying to measure the fraction of the excitation to the Rydberg state, and this we are going to do for higher and higher principal quantum number. And the objective of this measurement is to look at the Rydberg excitation dynamics to explore the universal scaling behavior in very strongly interacting cold Rydberg ensemble. So also we are measuring a second order correlation function of the Rydberg atoms, which will give the signatures of Rydberg blockade. So the next step in our experiment is to trap single individual Rydberg atoms in an optical tweezer, and here we are using a 850 nanometer beam to focus the optical tweezer beam to 1 micrometer, where we can trap single Rydberg atoms. And the objective of having so small focal spot is that if you have more than 2 atoms, they will have collisional blockade. There will be collisions among themselves, and both of the atoms will go out of the trap. So this will ensure that there is only one single atom in the optical tweezer. So we have, for this purpose, we have a high numerical aperture lens inside the vacuum chamber to create the optical tweezer. So this is our optical setup, which is all in place to make the optical tweezer using the 850 nanometer beam, and to probe the atoms using the fluorescence imaging, we have this 780 nanometer beam. So the single atom trapping actually enables exploration of quantum physics at the microscopic level. And this was evident from the fact that the Nobel Prize in 2012 was awarded to Serge Haroche and David Weintraub for groundbreaking experimental methods that enable measuring and manipulation of individual quantum systems. So with this optical tweezer, the idea is to have individual Rydberg atoms in the optical tweezer and to excite them to giant Rydberg states, and which will enable the realization of quantum entanglement due to the dipole-dipole interaction between the Rydberg atoms. So as we all know that in a microscopic system which follows the single particle physics, and in the macroscopic system which follows the many-body physics, so what happens in the mesoscopic regime? So the idea is to have assemble atom by atom this optical tweezer with individual Rydberg atoms, and to explore the mesoscopic regime all the way to the microscopic regime to explore the scalability with a 2D array of Rydberg atoms. So it's not only useful for exploring quantum technology, but also to explore very interesting fundamental physics. For example, you can have the Rydberg atoms with long-range interaction arranged in a triangular lattice to explore antiferromagnetic ordering with square or triangular array of Rydberg atoms to explore quantum simulation of this many-body physics and address open questions in quantum magnetism. So as I had said that quantum sensing with Rydberg atoms is a very promising field because of this large polarizability of Rydberg atoms, which goes as n to the power 7. And this makes it extremely sensitive to small DC or AC electric fields. And so we can use quantum tricks such as squeeze states to overcome this standard quantum limit and probably reach the Heisenberg limit. The state of the art now is 10 microvolt per centimeter per square root of hertz. So with quantum sensing using individual Rydberg atoms, we hope to reach or maybe go beyond this state of the art value. So I come to the end of my talk. So I summarize what I discussed. So I explained the exotic properties of Rydberg atoms, which makes it a very promising candidate for applications in quantum technologies. And I talked about our recent results on high sensitivity magnetometry with Rydberg atoms. And we have observed the Rydberg excitation in cold atoms. And at present, we are measuring the Rydberg excitation dynamics to explore the universal scaling in strongly correlated ensemble of cold Rydberg atoms. And I gave a future perspective on quantum information and quantum sensing with cold Rydberg atoms. Thanks for your kind attention.
Yeah, so I think you mentioned it, but I remember it from your earlier talks. But just to understand exactly what is this property of this rapid response, why does that happen? I mean, you said because of the switching, you can use it as a switch and its responses can be very quick, right? You said.
Yes, yes.
I didn't understand why exactly, because it is at a high energy, this thing, but you're also keeping it there with the laser, right?
Yes. So what I said is that the switching can be very fast. I mean, it's a technical reason, is that the lasers for the Rydberg excitation can be switched very fast within a fraction of a microsecond. So whether it will be in Rydberg state or not is decided by that laser. So that's why, since the laser can be switched extremely fast, that's why whether it's in the Rydberg state or not, we can control it very fast. Yes, yes, yes.
So, when you talked about the properties of the Rydberg atom, you mentioned the fact that it has a long lifetime, right?
Yes.
So I was just wondering that's I mean, it's an electron very far high, and so it should be very easy to get rid of it very quickly, right? So how
Yes.
is it that the lifetime, I mean, I can imagine the lifetime of it coming down is okay, but it getting ionized in the sense that the electron totally leaves the atom. That
No, it's just short of ionization. It's
no, I
very,
know, but
yeah.
then it would take very little to ionize it.
Yeah, but it's not, I mean, it's not straightforward. I mean, just with the ambient,
So you have to protect against the environment, right?
Yeah,
I mean,
that's
so the
always
point
protected. I mean, our experimental system are always protected against environment. They are in a vacuum chamber or in a closed system. They are shielded using a mu metal shielding, so that there's also no ambient magnetic
like
field
RF
or
leaking
any
in can
stray
also do
field.
that,
Yeah,
right?
there's enough shielding done so as to protect the atoms from the external electromagnetic field. And for the lifetime, so at very highly excited Rydberg states, so de-excitation to the nearby Rydberg states is easy. It can be done just with the ambient black body radiation. But the overlap, the wave function overlap between the highly excited Rydberg state and the ground state is very less. So if you look at the decay rate, so the decay rate to the nearby Rydberg state is much larger than the ground state. So that makes the lifetime extremely high.
So it remains somewhere
Yes,
out there.
somewhere in the Rydberg state, but not to the ground state.
And typically in seconds, how much is it?
So depends on the principal quantum number.
Yeah,
but
the ones that
I'll give you
achieved,
an
say.
example. At n equal to 80, the lifetime is like 600 microsecond as compared to ground state atoms, which are like 28 nanoseconds. So you can see the difference.
So can you please explain what you are showing in high sensitivity magnetometry?
Yeah. Yeah, so here we are saying that in a particular configuration of the coupling beam, we are seeing much higher sensitivity.
You have multiple Rydberg atoms in the system now?
Yes.
And you are applying external magnetic field?
Yes, yes.
And that field you have applied there,
Yeah.
and you have two beams, one of course probe and one your this coupling beam.
Yeah.
And then what are you doing?
So actually there are three beams. So we are exploring both coupling beam in both the counter propagating as well as co-propagating configuration.
So coupling beams are
two of
right?
them.
Yeah,
So,
that's fine. Yes.
so this one is corresponding to the counter propagating coupling beam, and this is corresponding to the co-propagating coupling beam.
And with probe frequency, you are looking for EIT signal, right?
Yes.
So So your claim is that EIT signal behaves very differently for
Yes.
counter and
Yes.
co-propagating.
Yes.
And you do not have yet
So
any-
we are making a quantitative theoretical analysis to understand, because this has to be taken, all the Rydberg excitation decay rates and
No, because even they are appearing at different frequencies.
yes.
So what is that reason for?
So this is because these two are at different coupling detuning. For example, I'll show you here. Here, this will explain. So when we have no coupling detuning, that means the coupling beam is exactly at resonance to the Rydberg transition.
Both the beams.
Yeah. So yeah, both the beams are exactly at resonance. Then we don't have separation between the co-propagating and the counter-propagating. But when we have a detuning of the coupling beam, now for the co-propagating beam and the counter-propagating beam, this two-photon resonance is satisfied at two different frequencies.
So are you then showing one with detuning and one without
So-
detuning in the next plot, for example? Like this one,
Yes,
the
yes,
counter-propagating with detuning
yes.
and co-propagating
Yeah, so
without
you can see
detuning.
this one is zero detuning and one is at certain detuning.
Means that is not shown in the probe frequency. Means you are saying that detuning in the coupling frequency.
Yeah, so if we have the coupling beam at resonance, you see that there is no division between the signals of the co-propagating and the counter-propagating. Only when we are detuning the coupling beam, then only they are different. As we increase the detuning,
So
you see.
I'm just trying to say that
Yeah.
even detuning may change that feature which are closer for the co-propagating you are saying versus for counter-propagating separately.
Yeah, so they are going farther, but the splitting is depending only on the magnetic field.
Yes, but even
Yes,
Can
yes,
we-
sure, sure.
Yeah, can we move on?
Changing
Yeah,
the
frequency
field.
sweep mode, yes.
So you change the magnetic field from what level actually?
So we are changing the magnetic field from 0 Gauss all the way from to 9.4 to Gauss.
Okay.
Okay, we have to move on. But before that, I request Kinjal to give the speaker token of appreciation.
Thank you. Thank you very much.
There's a slight change in the schedule. Next speaker is Prabhu from EEG. The topic is nanohertz gravitational wave detection using pulsar timing techniques.
Good morning, everyone. I'm very glad to be here and also very glad to see the front page of our program sheet that you have chosen, and it's a very nice, iconic picture, and the last year picture on the right side, and both are extremely good. And for some reason, the canvas has colorful trees, including the one which you see which blooms almost, if you have noticed, every year around this February end, and this year slightly delayed. Canvas full of colors, and it probably is what excited Raman as well, and he probably intentionally planted them. So Chitra Chandra Balan's note there, which says when they met in 1965, Raman spoke to them about a lot of things and also about color. So probably the canvas has a very bright and nice, colorful trees if you pay attention to. All shades and things like that are there. So thanks. And now going into the topic today, I will briefly give the concept, and I will give it from the point of view of how we build instruments. And the way it is put out here is in a manner that I would go to give some background and efforts towards detecting this gravitational wave, and overview of techniques of pulsar timing array. Of course, my interest started from this same table where we gave journal club talks for the LIGO squeezed light based experiment that when they were talking about. And recently, there were some work that we did with the UGMRT, and that has enhanced the connectivity with this work. So, gravitational waves is a harder subject in some sense, somewhat similar to the infrared astronomy people suffer from. Everything around us emits infrared, and you have to go to space. gravity, everything around us has some influence on the experiments we do, harder, and the constants are defined with not as much number of digits accuracy and things like that. It is a disturbance to what we think about the space-time metric. Time, from an engineering perspective, is a clock, but conceptually it's in our mind, and we define it. And so it's a complex subject because time, gravity, mass, they are sort of connected. As we go, an accelerated mass and the disturbance to the location, asymmetry, perturbs this space-time metric that we saw. It's a nice toy in your mobile phones. If you search for that, you can actually create another binary and see how it gets pulled in and so on. So it's basically an intuitive thing to feel how things happen. And this disturbance propagates as transfer waves at the speed of light, although it's the weakest it has as compared to electromagnetic waves. It's the weakest force, but still it can go all across. Then nothing seems to stop. We don't know quite well how we can probably counter in the labs. We can stop electromagnetic waves, we can shield Faraday cage, but this force is very different. And there are two polarizations, somewhat similar to electromagnetic waves, but at 45 degrees to each other. And the way the wave propagates, fortunately it's weaker, and if it goes through me, I would get expanded and contracted as it goes through, and that's the way it passes through. First indirect confirmation of this gravitational wave existence came from again pulsar astronomy, and the double neutron star system was timed, and again a timing experiment where they were able to see the orbit shrinking as predicted by the general relativity predictions. And that was the first detection. Taylor was also here giving the talk after his Nobel Prize, and which is very remarkable at that point. And so pulsar timing is not a new subject, so it has been happening quite a long time. But direct detection came through LIGO, Earth-based interferometers, which we all know. It's a long interferometric arms, 4 kilometer wide. And these interferometers work basically on the very textbook principles where there can be interference when there are two mirrors kept orthogonally and then they are perturbed. We can get interference fringe patterns. And from the patterns and the amplitude, we will be able to make out what happened to the space-time in between them. But it comes, this is again a 2014 detection pictures that I put just to show what do we see in the form of fringe. I like to see signals and their interpretations in the form of, how do you analyze the signals and so on. So this is very, very interesting signal, and the kind of chip that we see were expected, and remarkable it is that they were able to predict what is expected, and they were almost getting whatever they were observing from. And there are more to it, and now there are several of these detections happen. The sources that emit such a very weak amplitude detections are coming from coalescing binary neutron stars and stellar-sized black holes, and the graph is increasing. There are more candidates than the actual confirmed ones, and the challenge now is to see where they are coming from, and can we do something and understand more about that polarization aspect, which is a challenge still. So basically all that we record is the combination of the two polarization amplitudes and their projection angles that decides how well the amplitude can get accorded here. So Going back to the limitations of the frequency range over which it can operate, they are sensitive to 1 hertz to about 1 kilohertz, going through our audible range all the way to a kilohertz, all the way to human voices. Okay. And the lower limit on these instruments set by gravity gradient, and the upper limit on these instruments are get by electronics. That's the best we are able to do. Upper limit is towards the higher frequency sides. Now, if you want to do a little better, or there, so which means what is shown here is the spectrum of the gravitational wave spectrum. In that spectrum, these instrument ground-based interferometers operate at the highest frequencies and longer period oscillations, they are able to detect them. But if you look a little further, there are other sources whose frequencies can not just rotating neutron stars and some smaller size black holes, but there are also other objects capable of producing much slower range frequencies, not falling within the range at which the LIGO can detect. Now these range of frequencies over which, now how do you go about? There is a space-based interferometer plan which is supposed to be several times bigger than in terms of the arms, interferometric arms, and travel in the space of millions of kilometers distance, three pair of instruments, each one of them is 2 satellites. They just come behind us something like 100 times far away from moon, a distance that far away. And the way they work is they transmit laser beams, whereas in the case of LIGO, the laser beam is reflected back and forth between the mirrors. Here the lights are sent across and then again sent from another source sends it to the next one. So there is a local reference, the light interference or anything happens to it is locally checked, not by bouncing back and forth, because the laser beams cannot be generated that powerful to get the multiple reflection back or even single reflection back. So the way it operates, a passing gravitational wave perturbs the space-time metric, and that changes the signal travel time between the 2 spacecrafts, 3 spacecrafts paired, and that perturbations, when it happens, one will be able to detect a passing gravitational wave. There are challenges there, more challenges than the mission is yet to go. I guess 2034 is still the time, or maybe around that time. But it works now on a frequency range which is much smaller, and it can go up to something like microhertz, close to microhertz range. Remember, LIGO stops at 1 hertz kind of a range. Going further, this is another animation just to show how the spacecraft would travel around. The blue is the Earth, and it's one of the biggest missions. LIGO itself is one of the greatest, biggest engineering marvel, with the mirrors and all other electronics supporting them and so on. This will be yet another biggest mission. Going further, going back to the pulsar timing array experiments, people have been worrying about how to measure small forces. Cavendish and large number of people have put theoretical prediction once the pulsars have come. This Russian author, I believe Russian author, and paper not always been quoted, people go for another author all the time, has put in all the formulation in the early 77, 78 work. Basically, one possible technique is to use the electromagnetic radiation travel time. Another one is to detect the time variation between pulses of electromagnetic radiation, which is basically pulsars, and study that difference, and from there we can actually detect the passing gravitational wave. So suddenly it opens up, it's a formulation, and basically we are looking at the difference between the 2 pulse arrival times. I'll go quickly into a cartoon. So what the proposal is to have a clock, and an observer looks at the clock, and the clock is at far away, and there's a passing gravitational wave due to some disturbance of the mass either accelerating or they get disturbed going around or spiraling and so on. So this clock is same as the laboratory clock. So we don't expect that to tick differently from the laboratory clock. The observer note down the observed time at every laboratory clock time interval L1, L2, L3, L4. So there will be a difference, shift due to travel time and so on. If you take everything into account, the only other thing that can change if the path is disturbed. That could happen when there is a passing gravitation wave that can come through this. That is what the paper talks about. Suppose we take, instead of one clock, we put more clocks and put them across in the sky at different places. You get a kind of tomographic view of the passing wave. And the observer notes down every clock. And there we have this experiment, pulsar timing experiment we reach. That's what it is. So you remember, it is not electromagnetic wave. The path is distorted by the different kind of polarization, the X and the plus polarizations. Now, and the signal that we receive, the observed time for every one of the clock, if you plot, if there is a passing disturbance, that would manifest in our measured time like a chip form. And at the end of it, if the mass that is going around is going to get into the black hole or they are going to merge, and there will be a higher amplitude as well as they cease to appear afterwards. There will be no more disturbance. So now, Kipthorne's explanation from the early 1977, nicely put in from his own paper, is there are interesting characteristics, information available in this chip signal. There is a binary motion, and we see a Doppler effect. And now it depends on the eccentricity of the two masses. If there's a 2 mass, 3 mass, based on that, we have this shape change that we encounter in many of the problems. One of the problems that we see a similar problem in searching for the orbiting binary pulsars, a problem that we have been tackling to produce a Fourier domain acceleration search for the SKA. So the change, it changes the shape of this nice looking one, nice looking chip. And now again the inclination is going to put in that little more additional change. Already astronomers know visibility kind of a peak amplitude differences, somewhat similar to that, but it is not exactly. The two amplitudes is going to play a role in deciding the amplitude based on their inclination in which we are looking at it or in the line of sight. So this is the basic, but the problem has more complexity, as you will see, and lots of information that can be deferred from these shapes. The challenge is to match the shape with a model and perfectly doing all these removing a lot of calibrating to make sure that amplitude changes and oscillation changes. None of them comes from the instrument or from the interstellar medium other than the gravitational medium. So I put a slide from my last in-house presentation where we were searching for the binary pulsar where the frequency Doppler, exactly similar Doppler shift, it doesn't get into merger. So we catch it much here as binary pulsars. And Doppler shift, and we built a set of 84 filters to deconvolve, to straighten this up, to know this is for searching for it. So basically the algorithms work to straighten up this curved line to straight line, otherwise the signal to noise ratio goes up. So there is an interesting aspects opens up from these shapes and an information quite a lot, including the chip mass of the system can also be derived from this. And when it is going to eventually, suppose we catch it somewhere here, we can also tell when they are going to merge into one system. So the Earth-based detectors catch things around here for a certain amount of time. We can see that before merger. So now coming back to the sensitivity levels of the systems, we have the ground-based detectors, space-based detectors, and the pulsar-based detectors here. So this is a strain. The strain given here is best, and you very weak signals can be detected by the LIGO. Although due to the frequency range, we are limited on the mass of the objects that are initiating those gravitational wave. That get decided due to the frequency range where we are in. And 2 minutes, I'm finishing. I have to now go quickly to finish up. So, and the pulsar timing have lower sensitivity, but we have possibility of detecting variety of things there. Okay. So now I'm going to rush through because the basics are covered. So we are looking at, as part of the gravitational wave detection using the pulsar timing array, the frequency range is microhertz to nanohertz. And basically we look at pulsars in the sky. They are nothing but clocks, and passing gravitational wave disturbs, and in the measured pulse periodicity, routine observation is required. Periodicity is embedded information about these perturbations, and a whole lot of processing care needs to be taken, including the interstellar medium delay, which we call de-dispersion, and time offset, and delay due to the solar system passing through when we observe and where the pulsar is, and time dilations due to a variety of reasons, Einstein's delay or Sapphire delay and things like that. So all of that has to be taken into account after doing the observation. So we do stand here in this regime here now with the confidence that we are able to observatories across the world, including our own observation from the GMRT, have put in what is known as timing residuals, the measured difference between the observed time and the expected time for a model of the pulsar. The clocks, pulsars are very good clocks, but they have to be modeled because they spin down slowly. So what is shown here is the difference. In these residuals is where the gravitational wave information. So it's only the Indian contribution is from 14 pulsars currently, but internationally there are quite a lot of people all the way as you see here. And there is a background radiation because there is large number of gravitational wave sources. One of the primary thing, like in the case of a CMB, first to detect the gravitational wave background signal, and only then a burst kind of signal, which is a transient event, can be differentiated from the background. So the name of the game is to find the Helings and Downs curve predicted by this group, which is expected to show angular variation of the background as seen by the pulsar timing arrays. So currently, observational evidences show we are close to it, and no publications have come because people are waiting to confirm reasonably from most of the observatories. And that's where we stand. And the current thinking is when SK comes up, the limit of where we are now is going to shift by orders. So the sensitivity level will go high. So I stop here at this point to take any questions.
Yeah, I have a naive question. So you mentioned about several clocks and all, and passing of gravitational wave. So in that work, how to ensure that all the clocks are synchronized?
Yeah, that's the problem. In this laboratory kind of model, I put a, actually it's even hard to do it in a cartoon like this. Okay, if you upload at different times, it will run at a different time. So I have to clone them, okay? Copy one and then clone them. So you'll find that problem not only there in real world, it is hard. So the clocks are not, the clock that we are talking about, pulsars, whose rotation periodicity has been studied, modeled, and their expected times are recorded. So we know when is it expected. They don't have
that paper you mentioned, that was a previous experiment in the laboratory, right?
Which one?
Yeah, this one.
Oh, this one?
Yeah, yeah.
No, the paper, I have cartoon with illustration.
Oh,
I extended the paper to a cartoon.
Oh.
It's not experimentally said
Oh.
that way. The paper directly talks about pulsars,
Oh.
and they work out all the formulation for how to calculate it.
Okay. Thanks.
I have one question. So you are talking about two polarization modes. So how do you define the polarization modes for the gravitational waves? Because I thought this is a tensor kind of.
Mass, it is different from the electromagnetic
Yeah. So
polarization.
yeah.
It's a mass perturbation. I think it is. You are probably in a better position to answer to this question than me. I think some of you in the first 3 rows.
Okay.
But I think it is coming mainly from the way the mass perturbations cannot be like a. It's a solid thing.
Okay. Okay.
So Earth has oblong shape.
Okay.
North-south diameter is smaller than the east-west. So this is a kind of a thing that thing which rotates naturally tends to form. So I hope
We have to move on. Before that, I request the organizer to give a token of
thank you.
appreciation. Please come side.
Thank you. Yeah. Thank you. Thank you.
Our next speaker is Dibendu Roy from TP. The topic is how to quantify photon-photon interaction for different types of light.
Okay, so let me begin by thanking the organizers. organizers. Uh, so I have posed this question, how to quantify photon-photon interaction for different types of light. And I will first tell you what I meant by photon-photon interaction, and then I will discuss a general framework which we have developed to quantify such photon-photon interaction for different types of light. So mostly coherent light, which can be like single photon, means Fox-state light or a laser source kind of. And our work is available in this article with Atul. Okay, so as I said, I will explain you what I meant by photon-photon interaction. So photons are quanta of electromagnetic field or radiation, and they are chargeless and also zero rest mass. Therefore, they don't scatter each other in vacuum, or they are extremely weak, means they have very extremely weak scattering. So that called Schwinger limit kind of. So beyond some high frequency of light like gamma ray and all those region, photon scattering is possible in free space, but that kind of scattering has never been observed for ultraviolet or higher wavelength. Still, I can make or create effective photon-photon interaction. We can create such interaction because photon interact with matter, and one can use such light-matter interaction to have effective photon-photon interaction, which I will explain you that how such photon-photon interaction in quantum electrodynamics regime. So that means with few photons and single atoms one can realize. And the main thing of my talk will be that photons quantum nature is important. So I will not talk, means one can discuss photon-photon interaction in classical regime also, like using Maxwell equation. But in this talk, what I am going to specify mostly that this photon-photon interaction which I am going to talk mostly in the quantum electrodynamics regime where light behaves as quanta or photon. So the 3 simple processes for light-matter interaction. So if I have, for example, a 2-level atom in ground state, I shine a photon on it, it is absorbed by this atom, and atom goes to excited state. Then depending on the excited state lifetime, this photon will spontaneously emitted, and the emitted photon will be will have phase and direction random. But then these excited atoms can be also stimulated to emit 2 identical photon, like in the stimulated process, which is very essential for building laser light, for example. So we can have then absorption, spontaneous emission, or stimulated emission. And I will use these 3 simple processes to describe how one can generate photon-photon interaction for few photons. So this I am trying to explain for 2 photon scattering by an atom. I am mostly restricting my atom and photon in 1D, and it will be clear why I am restricting it in 1D in confined space. So we have this light tau s lifetime, which I just explained, that there is a spontaneous emission lifetime, and if we have two photons which are arriving on this or arriving at this atom, two-level atom, beyond this tau s interval, so then what will happen, first photon will be absorbed by the atom will go to excited state, and the second photon will wait before it spontaneously emit the photon. So such process is independent scattering of photons, and photons are still uncorrelated. So all superposition principle, everything will work for such light scattering. But now if two photons come within this tau s interval, or for example here I am showing they come simultaneously. So now two photons cannot simultaneously excite a two-level atom. So then this two-level atom behaves as kind of a hardcore interaction for these two photons. And because of this hardcore interaction, you will have kind of a correlated scattering of photons, which for example for such simple system one can solve and get exact scattering state for those color which I have shown here. And one interesting thing about it, that even frequency of photons can change. So I have shown here by different colors. So for example, originally I have two photons in green, and now you have photons, of course energy, total energy or total energy means here frequency of sum of frequency will remain conserved, but it can become like red or blue, though it's difficult to have such a big change, but the frequency of scattered photon can become even different color, and that kind of create fluorescence in a medium. However, this photon-photon interaction for few photons and single atom is almost negligible in free space, and the simple reason is like this scattering, which I can say the probability of exciting one atom will be order of sigma by A, where sigma is like scattering cross section of an atom. So one atom will be order of 10 of angstrom, not for the Rydberg atoms really, 10 of angstrom, and for visible light the A will be order of, the transverse area of this light will be order of, let's take lambda square. So in this case sigma by A will be 10 to the power minus 4 or minus 5 order. So it will hardly scatter light. By a single atom you can hardly scatter light. So if I block by a single atom this pointer will pass through, the light through the pointer will pass through, it will hardly scatter. So the light matter interaction is very negligible in free space. And how to create strong light matter interaction is the one of this field which was developed long back, almost now 30-40 years, cavity quantum electrodynamics, where one confine one atom and the let's take single mode of photon inside optical mirrors which forms cavity or resonators, and then photons scatter or reflect back and forth between these two mirror surface, and by multiple scattering you will have effective strong interaction G. So this G, the scattering or G will be related to this ratio actually sigma by A here. So G depends inversely on the volume of this cavity. So smaller volume you will have stronger coupling. And this kind of cavity QD setup has been also created with a solid state system like superconducting circuits. So this is like a transmission line waveguide. Or what we have three superconducting plate, and the middle plate carries the electromagnetic field mostly in the microwave regime, and these two gap creates the mirror kind of, or the confinement. And you have this superconducting qubit which can be very high, whose dipole moment can be very high. So that means dipole moment high means the sigma can be very large. So what we have achieved then, sigma is large, and because of this confinement of light within this waveguide, A is small. So sigma large, A small, and you can have stronger light matter coupling. And now the question is, do we really need that gap? in this middle plate. Of course, gap is required to have kind of a cavity, but the cavity also has drawbacks because the photons which become interacting within this cavity, they comes out from this cavity stochastically, and also the cavity determines the bandwidth of the photon which are coming out. So and those are bad for doing any optical devices out of this interacting photon, because what we want to do, control one photon motion by another photon. So we make interacting photons. We can have many body theory for photons, like maybe sometimes even gravitational wave, and we want to create that without any having gap here, and that has been also realized, and people have seen that, oh, I still can have very strong light matter interaction because I can even go confinement deeply in the sub-wavelength size, and because of that, and because again huge dipole moment of these artificial atoms, I can have very strong light matter coupling, and I can have these waveguide QED systems. And my talk will be mostly about this waveguide QED system. What I am mostly interested, I am interested to study the scattering problem and try to understand from the scattering problem the properties of this photon-photon interaction. So what we will do, we will inject some light which can be in coherent state. As I said, it's like state of an ideal laser light, which is a superposition of Fox state photon, or in Fox state, which has definite number of photons. So we can have this input light, let's take in coherent state or Fox state, and we calculate transmitted or reflected photons, or the wave function for reflected and transmitted photon, and one can do this. So exact multiphoton scatter state one can calculate for these systems, and once we know those, we can use them to understand what kind of photon-photon interaction or what kind of nonlinearity in this medium has been created. So as I said, that nonlinearity is not something new for light. It has been created almost now 50 years, and it was created initially using very high intensity of light, so mostly in the classical regime of light, using different nonlinear medium, and you mostly describe those systems using Maxwell equation. Of course, now you have to change the polarization density, where we have to take care that the polarization density, because of applied electric field, will respond not only linearly but also non-linearly. So chi1, the linear susceptibility coefficient, and chi2, chi3 are non-linear coefficient for this polarization. And if you have a spatial inversion symmetric system, chi2 will be 0. So you can, if you want to truncate above third order process, you can show that polarization density depends on this factor. So we can have a effective chi susceptibility for such a medium. And what we do, we try to understand this chi for our quantum nonlinear medium. So we will try to calculate such susceptibility from this microscopic calculation. So as I said, we still want to calculate everything from the scattered states. So this has been shown, we have shown. So the transmission amplitude depends on the susceptibility, and this susceptibility is the effective susceptibility of the medium, which depends linearly as well as non-linearly on the electric field. The electric field here is omega p. Actually, omega p related to electric field, EP. So what we calculate, we actually calculate the phase of this transmission amplitude and take the linear part, electric field independent part and electric field dependent part separately for different type of input lights. But the problem was that the problem was that if you have coherent state light, it's easy to know what is the transmission amplitude, and even experimentalist has measured that for multiphoton state. But if you have like this Fox state photon, which have two Fox state photon injected in from the left, so it's difficult to know what is my transmission amplitude phase. The reason is I have there three processes, and both this process and this process contribute for the transmission amplitude. So then how to calculate that transmission amplitude? We figure it out again a framework based on this well-known quantity which called first order correlation function, but of course we have to measure it differently, at least theoretically that's what we found, that this is the first order correlation function which is mostly measured in all interferometer. So what we have to now, when we are calculating what we do, this first order correlation function which are written in terms of this field of the electromagnetic field, we take one of them before it scatter, another after it scatter, and calculate it for different kind of light source. So for example, this is for coherent state light and this is for 2 Fock state photon, and this is the transmission amplitude, which if I expand it in order of omega p, which is EP, then I get linear component independent of electric field, nonlinear component which depends on intensity of the light here, and then higher order components. Now if we even calculate that for 2 Fock state photon, we again see the linear component is same. That's not surprising, because finally in the absence of any kind of nonlinearity they will be same. But now nonlinear part for Fock state case, I have similar contribution like this. Of course it's changed by intensity now here for one photon, not the full intensity of the coherent laser, but then there are also extra terms which is small, but there are extra terms here. And we kind of calculates this thing means separately for different kind of light sources and try to measure or propose what will be the KR coefficient. So KR coefficient generally measure what is the effective interaction one is generated in this medium. So we got an expression for KR coefficient, because now my medium is nonlinear, so refractive index also depends on intensity of light. So this N0 is intensity independent component, N2 is the quadratic order on the electric field or linear in intensity, and the coefficient is that if I take difference between these two, that coefficient like N2 will be related to KR coefficient, and we calculate that. And what I am trying to show here is these different phases. So different phase means the total phase and then the linear and non-linear part of those phases. So the total phase is this blue color, linear part is the green color, and the black color is the non-linear part. Okay, so maybe it's just showing something, it's still not clear what really they means. But still one thing one can see that when you are near resonant, because this is the detuning of the incident laser from the 2-level transition. So near resonant you have strong non-linearity in the medium, which is shown by this black curve. Now the similar like interaction between light can be done even if you have two different light sources, not single source. And that is what has been done with a 3-level system, where one level is driving one beam, one transition is driven by one beam, another transition is driven by another beam, and experimentally the phase change, let's take phase change in the probe beam due to the drive beam was measured, which also we calculated, and this is this curve that which shows that what is the nonlinearity created in this system. And as you see in experiment, they claim single coherent state light which is in very weak intensity can change another light phase by 25 degree. So huge change in the phase of one light by another light. And why is good? Because then we can control one photon motion by another photon. So it becomes a nonlinear medium like what we discussed for electronic mediums with Coulomb interaction. And this interaction even also can be shown, can be attractive or repulsive. So with this I will finish. So what I have tried to say that we have introduced a general framework to quantify such photon-photon correlation, which can be generated by strong light matter interaction for few photons and few number of atoms, and this is reported in this paper with Atul. And to know more about all this waveguide QD system, this is our review article. Okay. Thank you.
Dipindu, I have a naive question. So in this case, so you used high sigma or scattering
Yes,
rate, and
scattering
that's the
cross-section.
only property of the waveguide cavity
Yeah, so
for
what
the.
we are doing, we are increasing sigma, decreasing A.
I
Okay?
got that. So my point is that, so when you use that special configuration for the waveguide system, so another general confusion I normally have is that the wavelength of the light is actually larger than the size of the cavity in that case,
Yes,
right?
actually
This is
that's why
different.
that we say that it's confined deeply in the sub-wavelength,
Sure, sure.
so beyond diffraction limit.
So now my point is that could that be responsible for the phase correlation rather than.
Okay, so my understanding is that it's due to this hardcore interaction at this atom, because as I write, two photons can become correlated via atom due to its inability to absorb more than one photon at a time. So if you bring two photons, like let's take I bring two different, means two photons with a delay. So generally we'll think, oh, I have now one photon exciting this atom to the excited state, second photon will come and stimulate this emission. So you will have stimulated emission. And of course in stimulated emission for indistinguishable photon, you will have also some kind of correlation. But here it's even more than that, because of this confinement and this hardcore interaction, you have stronger correlation.
It's the same thing. Maybe it's a trivial this thing. So this when these two photons are coming simultaneously or within this tau
Interval,
layers,
yeah.
so these are still uncorrelated
Yeah,
photons.
initially
right?
they are,
They're still uncorrelated. So what prevents actually that one of the photon excites the
yes, exactly,
atom to
Sanjeev.
the.
So that question bothers,
Yeah.
that out of two photons, of course they are written in a symmetric form because photons are bosons, so we have a symmetric form. So which photon will you choose? And
mean,
when you try to
with
solve, so
with
this
what-
actually,
Yeah, I understand it comes out from the equation. Or
yeah, you
something.
solve actually with answer. Okay?
Yeah, yeah.
So you
But
solve.
is it not like with some 1 by square root of 2, you take one and the other one? Like, I mean, if both,
Yeah, so that
both
is
can.
what even Einstein theory of stimulated emission says. Like I have just one photon goes and excite the atom, another photon does the stimulating. That indistinguishability of the photons will of course create some kind of correlation, but it is more, and that is the main message. That
So
due to the hardcore nature.
So it's like a two photon symmetrized way.
Yeah,
Some-
of course, photons are
Okay.
symmetric. Hardcore means, let's take, we have two bosons, just a massive boson. Okay, so then they repel each other, right? After beyond certain distance, they can't come closer to each other. No, hardcore means I'm saying like massive boson, not photon. And here that nature is coming. Okay, maybe
So
mathematical.
maybe if you,
No, mathematically I just
yeah,
answer
maybe,
mathematically.
maybe. So basically, mathematically, how
Yeah.
does this
So
two
what is
photon coming
the
different?
mathematical description? So this is, let's take simple model which called Giants coming model, and I am mostly bothered with this kind of Hamiltonian, which, so what I will write for sigma, so sigma is, okay, so I have two level system, ground state and excited state, and sigma is like, and sigma dagger other way. Okay, so this is this Hamiltonian for two level atom here, you ignore gamma now, and then what we have, this Hamiltonian I can write actually some kind of, so I will replace all sigmas by just simple boson operator, but now hardcore, I will explain what is that. So I am using already A, so I write B. So what it will happen, I will write, I will explain. So the same Hamiltonian I will write as So what I have done, I replaced two-level system by an anharmonic potential. Okay, so this is two-level energy, energy omega E, and this is the anharmonicity. U tends to infinity is exactly two-level, right? Because anharmonic potential is like you have energy levels like this, and this difference from this determined by U. So U tends to infinity, this level goes out, it becomes two-level.
Okay, we'll have to move on. Sorry. I request the organizer to give the token of appreciation. And let's invite the last speaker, Ekta Sharma. She's an A&A visitor. Her topic is role of magnetic field towards the dynamic of a reflection nebula.
Okay. Good morning, everyone. First of all, I would like to thank the organizer for giving me an opportunity to present my work today. So I'll be talking about the magnetic fields towards this reflection nebula, which is NGC 7023. So first of all, I'll start with the general introduction. So when we look up in the sky is full of, night sky is full of a lot of stars, but we also see blank spaces in the sky. This looks like that they are blank spaces, but they are nothing but the interstellar clouds. And these interstellar clouds, they when they fragment into dense cores, under the conditions of their gravitational stability or instability, they can form ultimately collapse under their own gravity and form young stellar objects, and finally going through different stages of stellar evolution, they can finally reach the stage of main sequence stars. So these molecular clouds, because they are made up of like hydrogen and helium, that's why they are these interstellar clouds called molecular clouds, and they are also called dark clouds because when you see them in optical, they'll appear dark, whereas once you go to little longer wavelengths, say this is Horsehead Nebula image, when you go to like near infrared image, this will, the emission, the cloud morphology that will start coming up, and then if you again see in much more longer wavelengths like far infrared, which is about 850 micron or 500 micron, then the cloud emission will be well seen, and you can find out that okay, this is the molecular cloud present over there. So one of the very like major challenges in star formation theory is that how do these stars form and why only certain number of stars are forming. So if we go with the concept of that all the material all the gas material which is present over there, that will fall under its own gravity and under the free fall, then the total galactic star formation rate for that gas mass should have been 200 solar mass per year. But that is not so. Actually, star formation efficiency is just 2% from the giant molecular clouds. That means there are factors which are actually trying to resist or delay the gravitational collapse, and these factors mainly, like studies and simulations have suggested that there can be magnetic pressure or turbulent kinetic energy, like I have shown here, that in addition to self-gravity, when the cloud evolves, just from the very primitive stage, that can evolve under the effect of magnetic field as well as in the effect of turbulence also. So yeah, this is in brief the different stages of star formation. Like there is a molecular cloud, and it can, depending on the physical conditions, it can fragment into different cores, and these cores then evolve to a protostar, and then there can be gas outflow, and then finally main sequence star. So talking about this particular stage of molecular cloud, so they are actually not spherical like with over the last 2 decades with the observation of Herschel space satellite. The molecular clouds are actually in the form of filaments. So these filaments are actually ubiquitous in the interstellar medium that are shown in like far infrared observations of Herschel satellite. This is one example of Taurus molecular cloud, which is like you can see that, so these filaments are actually like the structures with aspect ratio greater than 5, and they have categorized them as in the form of high density filaments, with the column density greater than 8 into 10 to the power 21, and then the subcritical filaments which has density less than 8 into 10 to the power 21 per centimeter square. So when you again zoomed up and see them in more longer wavelengths like 1.25 millimeter, then these filaments you can see that there are starless or protostellar cores which are embedded in these filamentary structures, which are possible sites of future star formation. And these cores, they are found to be associated with these filamentary structures. So that means these filaments and these cores, they are very important in understanding the star formation theory and how do they evolve to cores. So then there are like different factors involving that I'll be explaining in my talk further. So before that, I'll just give a short intro about the composition and the content of the molecular cloud. So we all know that they are made up of, they are molecular. So that means they are made up of hydrogen, molecular hydrogen or helium. But at the temperature of molecular clouds, which is typically 10 to 20 Kelvin, this molecule cannot be excited because the temperature is about 512 Kelvin to excite this molecule. So the only way to observe them and to find out the emission from the cloud is indirectly through by observing the trace gases, which is N2H plus, HCN, C18O. And typically the composition and the content of a cloud is usually like this. For example, you're starting from the outer boundary of the cloud, starting from 15,000 AU. So there are mostly carbon-based molecules, and then as you go deep inside, then these carbon-based molecules, they get actually depleted on the dust grains, and then there are nitrogen-based molecules more. So as it goes more towards the center, where the density is increasing to the stage of like 10 to the power 6 per centimeter cube, then nitrogen-based molecules are more. So basically, we observe CO or N2H plus to find out the density of hydrogen, what is the actual content of molecular hydrogen present over there. Okay, so I'll be talking more about like how the galactic magnetic field is playing role towards this molecular cloud, taking one particular example. So this is a all sky Planck emission map, which is basically dust emission map. So you can see that our whole Milky Way, it has like, so the scale shows actually the density of magnetic field strength, and the lines show so the direction of these lines, it shows the direction of magnetic field present over there throughout the galactic plane or above than that. So it has really provided new insights into the structure of galactic magnetic field and the properties of dust, as it is like the main reason for giving the polarization information. Also, this is one of the example for Orion molecular cloud, which is at the distance of 450 parsec, and you can see that there is a well-aligned morphology of the magnetic field. So these lines are actually talking about, they are actually showing the density or basically the strength of magnetic field that is present over there. So the typical strength on the galactic scales is 10 to the power 20 microgauss, and by studying the dynamics over a whole, we find out that it is important actually in regulating the star formation efficiency. Okay, so before moving further, so there is like when the filaments, they evolve to protostar going through the protostellar cores or the pre-stellar cores, there is one more factor which plays role, which is called like the stellar feedback. And there are two types of feedbacks that we can study. That is, one is positive feedback, another one is negative. So positive feedback is actually, it helps to increase the star formation efficiency and increase like the birth of first generation of star and the second generation of star by compressing the material present in the surrounding molecular cloud. And then there's negative feedback, which can actually completely disperse the cloud and quench the star formation efficiency. So I'll be talking about more about magnetic field and also how does it affect how does it change in the effect of stellar feedback. So this is one example where there is no stellar feedback. So this is Taurus molecular cloud and Musca. So these two clouds, they differ in the form of their star formation activity going on. It has lot of young stellar objects already present, and this is a quiescent molecular cloud which is not having any star formation activity going on. But as you see that, So these lines, they talk about magnetic field lines, and the color scale is actually the density or the emission from the filamentary structure of molecular cloud. So you can see that the magnetic field lines, they are actually kind of perpendicular to this long structure, and similarly in this. And it is not having any kind of like the stellar feedback present over there. So they may be responsible in actually guiding the material from the low density towards the high density of these filamentary clouds. So the main mechanism or how does it affect the magnetic field, the protostellar core, is actually through the ambipolar diffusion. So this ambipolar diffusion is nothing but ion neutral drift, which takes place at the time scale of 10 to the power 7 years, and which is much higher than the free fall time scale, which is 10 to the power 5 years. And this is basically the decoupling of ion and neutrals. Usually the magnetic field that is coupled with the ionized interstellar medium and as well as the neutrals through collisions. But because of ambipolar diffusion at the density of 10 to the power 5 or 10 to the power 6 per centimeter cube, when the cloud starts or try to collapse under its own gravity after the density increases, then there is decoupling of the ions and neutrals, basically trying to resist the gravitational collapse. And that is basically called magnetically dominated star formation, where the magnetic field is so much high that it resists the overall collapse and delays it, and therefore the overall time scale that actually increases. So yeah, that is the one that I was like talking about, and this is one example. And the consequence of ambipolar diffusion at the density of 10 to the power 6 is hourglass morphology. So these lines, red lines, are actually magnetic field lines, and these are ions encircling around line structure, and then there are neutrals. So you can see that magnetic field lines, they have actually pinched towards the center and resulted into hourglass morphology. So how do we observe magnetic field? So the technique that we use is basically polarimetry or polarization, and to study molecular cloud magnetic field, we use two techniques. One is background starlight polarization, another one is thermal dust emission. So this is basically to study the magnetic field structure in different scales and at different density regimes. So at the optical extinction, so the optical extinction is basically dependent on the density, the column density which is present over there. So the region where the density is very less, basically 1 to 2 magnitude, the extinction, in that case, polarization of background starlight is the main mechanism. And when the background starlight, it passes through the aligned dust grains, which are oriented along the direction of magnetic field, then the resultant light that we get is actually polarized. Why? Because these dust grains, they are not symmetrical, they are aspherical dust grains, and there is a preferential selective extinction of the light while passing through these dust grains. And the component of the polarized light that we get, that is parallel to the magnetic field component. Whereas when you go to the density of the extinction of 10 to 20 magnitude, then the magnetic field is actually perpendicular to the polarization angle, because it is based on the emission from the dust grains, not the extinction. So these two techniques we use. So I will be talking about mostly polarization of thermal radiation from the dust grains. Okay, so this is a neutral hydrogen, column density of the hydrogen over our Milky Way, and this is Cephas. So these are different distributions of the clouds over the sky, and this is Cephas constellation. So when you look at smaller scale, this Cephas constellation, I am picking up this one particular interesting region called 1172, 1174, and when you see more zoomed up version of this, we find out that, okay, so they are like different wavelengths. So this is in the Planck 353 gigahertz, and this one is Spitzer 3.6 micron image. So this particular region that I am studying called reflection nebula called NGC 7023, and this is lot of star formation activity going on, and the distance is 335 parsec, and so basically, this is kind of a butterfly structure where there is a cavity on the western side, but lot of emission on the left side. So what I want to, okay, I'll just talk about the, yeah. Oh, okay. Thank you. Yeah, to study the magnetic field in the reflection nebula, I've used James Clerk Maxwell telescope and with these many hours of observations and compared it with the Planck satellite polarization using at 353 gigahertz archival data. Yeah, this I've already like mentioned, and this is like one example for the magnetic field under the effect of stellar feedback. So, okay, I'll directly go to the our source study. So, right, so these reflection nebula, they are actually host sites of recent star formation going on, and they usually talk about that triggered by intermediate or high mass stars. So, basically this reflection nebula, it has a star towards the center, which is basically ionizing the material through stellar winds and the radiation pressure. So, I want to know that how is the magnetic field under the vicinity of this star is changing because of this stellar feedback. So, these are the results. So, you can see, so like in my previous slide I mentioned that the magnetic field is like perpendicular to the filamentary structure, whereas in this case, which is under, so this is a column density image and for the whole nebula, and I am looking just at the vicinity of the star. So, this white star marks the location of central star, and you can see the magnetic field structure. So, this black line is actually kind of average of the polarization vectors. So, this yellow lines, they are the polarization vectors. So, you can see the magnetic field has got reordered or reshaped, whereas it had a particular direction perpendicular to the structures earlier. So, these lines, yellow ones are the Planck polarization data, and this one is the JCMT polarization data at the resolution of 14 arc second, and this one was at 7 arc minute resolution. So, what we found out by comparing it different wavelengths, that the magnetic field which has two different distribution angle of polarization, that has got actually I won't say, okay, not random, but the dispersion has got higher because of its curved morphology, and this is the distribution that we got. So, the green one is from the results, the observation that we are studying. The dispersion is too high, that means we cannot apply our standard method of finding out the magnetic field strength. So, we adopted different techniques to get the magnetic field strength in this region. So, what it says, okay, so what it says that the magnetic field at the scales of 7 arc minute resolution, which was having a particular orientation of about like 135 degree, that has now that has got reshaped, and that could be because of the stellar feedback. To quantify that, so like, yeah, that's what I said, fields can get reordered in the presence of stellar feedback, and that could be because that the ionization pressure, radiation pressure from the star, that might have compressed the magnetic field lines under its vicinity and increased the magnetic field strength. That we have found out also, that the clump that we are studying, the magnetic field strength we found a 149 microgauss, and the envelope scale which was using optical or the Planck polarization data was 42 microgauss. And the overall clump is magnetically supercritical. That means magnetically supercritical means the magnetic fields are strong enough as compared to the mass of the clump. That means that it is able to stabilize the overall clump, and it will delay the gravitational collapse, and it is not under the state of infall or completely infalling the material under its own gravity. And I am like still working on the energetics of the nebula. So, yeah, that was all. Thank you.
Questions?
What is the main factor which decides the morphology of the magnetic field?
Okay. You mean like the gravity or?
Yeah.
Okay. So, the morphology of the magnetic field can get reordered. So, it's basically dependent on the gas density present over there, and also if there is like the high radiation pressure over there, it can compress the magnetic field lines over there, and that can decide that the magnetic field which was earlier, say, one particular polarization angle or one magnetic field that can reordered and get completely reshaped because of the feedback. But if feedback is not there, stellar feedback, and feedback is not there, then in that case it can only couple with the neutral or the ionic material over there and just guide the gas along the field lines without any effect, any external agent. But in some cases, if the feedback is too high, like this is some intermediate mass star, if there are OB type star, very energetic stars, 25,000 Kelvin, if it is in the vicinity, then it can completely distort also. So the line which was reordered or one particular direction, it will be just random, like there will not be any particular direction of it, not even the curved morphology or the reshaped one. Yeah.
Any object where magnetic field comes, what are the normal causes why it arises basically? In the sky, is it the same as how Earth has magnetic field or something else?
So it actually started with the seed field which was there, and then it got amplified because of different processes in the interstellar medium. So maybe because of like the gas motion coupled with the gas motion, or the density increases. So different factors are playing role in changing the morphology. So at different places, the strength as well as the orientation is different. Yeah.
Okay, end of this session. I request the organizer to give token of appreciation.
So Sevanti will present tuning of encoded memories in adhesive granule gels by an external drive.
Good morning, and first of all, very wonderfully organized meeting, so kudos to the organizing batch, and thank you for giving me this opportunity to present my work here. So a lot of terms in the title, but let's move slowly, baby steps. So memory formation. So what is memory? Memory is it's the ability to remember something that has happened in our past. Very simple, right? Now, turns out that systems which are far from equilibrium can retain a memory of their past perturbations or preparation history and so on. And lucky for us soft matter people, a lot of our systems happen to be out of equilibrium. So we get to see these very interesting memory forming abilities. Additionally, we can also get very important insights into the microscopics of such out of equilibrium systems through such memory formation studies. Okay, so this is one of the reasons why it's interesting to study memory formation in physical systems. And well, here are some examples of systems which show such memory formation, and also of what kind of stimulus we can encode and we can read out from these systems. And the highlighted ones are the regime in which I will be, in which I have been working and in which I'll be presenting now. And I'll come to the details in a couple of minutes. And this is a wonderful review article on this topic, which can be, it's a very good read actually. Yeah, moving on. So how do people typically encode memory in systems? So a very simple protocol is the following. So you have your system and you perturb it cyclically, okay? So it can be back and forth. It can be a sinusoidal or a triangular wave or a sawtooth profile, anything, but you're going back and forth repeatedly. So the system will evolve under this perturbation and it will reach a steady state, thus encoding a memory of the amplitude up to which you have cyclically sheared it, okay? Now, how do you read it out? So you image the system stroboscopically. So which means that before and after every cycle, you take a snapshot of the system and then you take a difference. So if it was a solid material and you take a snapshot after the deformation, it would be a completely dark, there will be nothing to see. But since these are particulate systems, there are like particles which can move with respect to each other, in these systems you can actually see some difference. So in the difference image you will be able to see some bright spots which will be like give you an idea of which particles have moved during that cycle. So you calculate the mean square displacement of such particles, and they are termed as active particles, and people usually plot the fraction of active particles as a function of number of cycles. And what they find is at the, for example in this case, so the amplitude at which they have been sheared is 3. So at 3 you can see that with increasing number of cycles of application, this system is developing a very sharp kink in the mean square displacement. I'll come back to this if it needs more explanation later on. But the point is, this is an, so you train the system, and then through imaging techniques, you can figure out whether the system has a memory through the training, okay? Now, what interested us is the following. So we checked the experimental work in different soft matter systems that has been done. And what we found is there are very few reports of systems which have shown a signature of the encoded memory in the bulk properties, okay? So for example, the 2 studies shown here, you can see that although there is some signature, but you have to really look very minutely, or you have to like zoom in to be able to see that signature. Now why is that important? So the thing is, if you are able to get a signature of the trained encoded memory in the bulk properties, then you can essentially end up with smart materials. You can train them as you need, as per your requirements, and they'll have the properties that you desire, okay? So that's the question we were asking here, that can we encode a stronger mechanical memory in the system. So before moving on, I'll just give you a brief idea of what our system is. So we make suspensions out of cornstarch particles. Cornstarch is highly amorphous. You can see there is no well-defined shape, and they are very polydispersed, large distribution of sizes, and they are hydrophilic, okay? So when you disperse them in paraffin oil, they experience a solvent-mediated adhesive interaction between each other, and they form aggregates. And turns out these aggregates are actually fractal, so which we confirmed using confocal imaging. And due to this fractal nature, at some point they are able to, like beyond a certain volume fraction, they can actually self-support each other, okay? So they'll form a solid, like they'll form a soft solid. And in our article we have actually like in detail we have studied the dynamics and the flow behavior of this system. And this is a schematic of our setup. It's a rheometer with a cone and a plate geometry and the sample in between. And this is our in situ boundary imaging apparatus. And I would like to acknowledge Yatindran for the SEM images, and Arslan for help with making this beautiful schematic of our setup. Now, so this is part of what I had shown in the last year's in-house, so I'm going to very quickly go over this. So we train the system with a triangular wave deformation for over 300 cycles, and we apply a readout something like this. So the idea is, in the readout, as you cross across this amplitude, if there is no memory in the system, there should be no changes, because in the perturbation there is no change, right? So it turns out through this training, this blue protocol, which is over 300 cycles, we see that the system evolves into a strain stiffening behavior. What do I mean by strain stiffening? You can see that towards the amplitude there is a sharp rise in the stress values, okay? So it's as if it's a strand that is being pulled to its taut length, okay? So anyway, so this is a steady state response that develops in the system as a result of training. And then when we take a readout, this red perturbation, we see that across this training amplitude, we see a sharp jump in the stress values, which is correspondingly reflected in the differential shear modulus as well. And in our case, we see that these signatures are pretty high. I mean, 5,000 Pascal, it's significantly high. You don't have to magnify and go inside to be able to see this signature. So very interesting, and this is also published, and some of the main results are over here, but I have already covered these. So the only thing that we will take from this work and move on is the following. So in the differential shear modulus, you observe a peak in our system, and the value of strain at which that peak is appearing, that is corresponding to the memory that is encoded in the system. Okay, we'll move ahead with this image, with this message, right? Now, The next thing is, if you have one memory encoded, can you also encode multiple memories? Turns out yes. So for our last work, we had this was our stopping point. We applied a protocol and we saw that yes, you can indeed encode multiple memories as well. But the point is, you have to apply the smaller one at the last to be able to observe any signatures of that. Okay. Now, for the current work, what we did is we used this protocol. So we are encoding this gamma t for 200 cycles. Then we are applying a smaller amplitude, gamma n, for some n cycles. And then we are taking a readout. So the idea is we should be able to see such multiple memory formation. Okay. So we have simplified the question now. We just want to see what happens to this encoded state if you keep applying the smaller one. So there is one simulation work on glasses that had made a prediction on this kind of a, if you apply this kind of a protocol. They said that if you do this, your mean square displacement at the trained state will become non-zero. So remember earlier I told you mean square displacement goes to 0. It becomes negligible if you have trained it properly. So here they showed that yes, so if you apply this kind of a perturbation, there will be some change caused in this encoded memory, but both the memories will still survive. You'll end up with multiple memories. Now for our system, turns out if you this is a readout curve in the first place. This is one readout for n equals to 10, and these are the two amplitudes that we have trained at. This is gamma t and this is gamma n. Okay, and we are looking at the k value at gamma t. Okay, since k at gamma t is supposed to give you the strength of the memory encoded, right? So we are looking at k of gamma t, and we see that there is a dramatic reduction in this value, and it reaches to almost 0, which means there is technically no memory at that point anymore, within like a few cycles. Okay, so this is interesting. Now we need to know why this is happening and why is it different from what has been shown for glasses. Okay, so now here's the thing. So if we plot, we have varied n from 1 to 60 in discrete numbers, and I'm plotting the k versus gamma, so that is the readout and derivative of that. So the derivative is plotted for different n values, and the dashed lines are the two amplitudes. So what we find here is the following. So this peak position, you see that this peak position is dramatically shifting towards the smaller amplitude, which is also reflected here, where the gamma peak, I'm plotting the position of the peak with respect to n. Now what is the consequence of this peak shift? So if I don't tell you anything about the protocol or whatever, if I give you just the information which we have from my previous work, that k, the peak of k, that position is what you have encoded into the system. And if with that information, if you look at this one, this peak position is somewhere around 0.055%. So then your estimation, or your what you will gain from that information is that the system was trained at 5%, which is different from both the amplitudes that it was subjected to. So it remembers a memory that it has not been trained at. So this is pretty fantastic. And turns out if we vary the different parameters, so we changed gamma t, we changed gamma n, and irrespective of all that, they all seem to, this peak shift, which we have defined in this way, delta is a peak shift parameter, they all seem to be falling on a very simple collapse, which means that the mechanism, irrespective of gamma t, gamma n, and n, the mechanism is same for all the cases. Okay. And one last thing that we could have changed is the shear rate at which we have applied the training at both the amplitudes. Okay. So we changed that also. And what we find is this peak shift is becoming more and more dramatic as you increase the shear rate. Okay. So in fact, you can see that for 0.04, so the initial one was 0.01, I should have mentioned that. So this is 4 times higher shear rate. You can see that the peaks have already merged, and now the system has only one memory. Okay. So what is happening? What is causing all this dramatic peak shift and all? So one thing we know for sure is that it seems this smaller one, because there is a shift with n, so we know n has something to do with it. So we are going to look at how this smaller amplitude, what is it doing to the system? So the easiest way to do that is to just check the response of the system as you are applying the number of cycles. Okay. So here I am showing you for 60 cycles, which is the extreme limit that we have gone to, at 2 different shear rates. And you see that in both the cases you do see some strain stiffening behavior, similar type of a evolution. But there is one difference which is very striking. In this case, you can see that the stiffening is comparatively milder, whereas in this case it is much stronger. To give you some more perspective, in the inset I have plotted, so the blue one is the last train state, so the 200th cycle, and the red one is the last cycle, so n equal to 60th cycle. So you can see how they compare to the train state. So sort of makes sense that at this point this will be able to overpower the encoded memory easily, more easily than this one. So now we have to think of what could be happening. So here's what we think is happening. So in this system, like I told you, there are fractal aggregates which can actually form strand-like structures which can withstand shearing. Okay. So now what happens is when you are applying the first training, the 200 cycles, so you have there will be some breakage of smaller strands and all that, and then eventually you'll end up with one or some strands which can withstand the maximum amplitude that you have applied. Okay, so they'll get taut at the maximum, and then you come back, they'll become floppy and so on and so forth. Now, when you are applying the smaller amplitude, yeah, 2 minutes, right? Okay, I'll be done hopefully. Yeah, so when you're applying the smaller one, what's happening is the following. So when you start applying this part, so you go till here, it's similar to what the training was, what it was going through when the training was being applied, initial training was being applied. But at the turning point here, there is a finite time of contact, right? So you have, let's say these are my 2 plates which are being sheared back and forth, and there are some broken strands, okay? So these broken strands, even if they come in contact, if you keep moving the plates, they'll again lose contact and they'll move on. But if at some point, if you give them some finite time, they can rejoin and make contacts, okay? So now once these contacts are established, they'll give rise to some formation of structures. So what we are thinking is the following. So you have a floppy strand like this, and it's as if you're putting a nail here somewhere, okay? You're making some structure here so that in the taut condition, it has to go over that nail. So then the taut length that you were getting initially will get shortened because it has to traverse this path, right? You're forcing it to go through that. So that's what we are thinking. And because at higher shear rates, why is this phenomena being more pronounced? That what we think is happening is the following. So in case of gels, it has been shown that if you shear them at higher rates, they will form, so these aggregates will break up and they'll form more homogenized aggregates. So you can form better structures from them. So our idea is, since you are applying a higher shear rate from the same situation, from the same broken down condition, formation of a better structure is more likely or better possible in case of higher shear rates as compared to lower ones, okay? So before I move to the conclusions, I would like to acknowledge 2 people who were very important to this work. Rajesh Ganapati, during the ICTS statistical physics meeting, which was also jointly conducted by members of RRI, he gave some very helpful insights into this work. And Nathan Kaim, who also helped with some insights into what could be the possible applications of this kind of a work, and my lab members, and I'll leave the conclusion while I take questions. Thank you.
Thank you. Questions?
Yeah.
So you
okay.
You showed that this polydisperse cornstarch particles can give rise to very nice fractal pattern.
Right.
So I was wondering whether you could really do a modeling of this, polydisperse cornstarch particles and how they, can form a fractal pattern. Whether theoretical modeling can be done or a numerical simulation which can, explain such a nice, pattern formation.
I see, okay. We haven't tried that, but that is a good idea. I'll find out if somebody else has done it or else if there's a possibility of us doing something in that lines. Thank you.
So when you are encoding multiple memories in the system, so initially you are encoding the larger strain amplitude you are encoding, and then the smaller strain amplitude you are encoding. So I was wondering if you make a signal of different rest amplitudes
Right,
and
right.
make a linear combination of that signal.
Okay.
And you train your system with that signal. That is not a periodic signal, but that is a linear combination of periodic signals.
I see. Okay.
So that will be a periodic signal.
We
And
can-
so will that work? I mean, so will you expect the similar kind of training? Will that
Memory
work in
to
the
be encoded?
Yeah.
I will expect memory to be encoded for sure. But if you're applying multiple memories, then which ones will survive will be dependent on the type of pattern that I'm encoding or training it with. But even with multiple amplitudes also, with the linear combination also, I think it should be possible. Memories will be encoded for sure, but which ones will survive the whole training is that has to be seen actually.
Got it.
Yes.
Thank you.
Hi.
Yes. Oh, Ion.
Let's ask one. No, this MSD, could you repeat? I think you said I
Sure.
missed. So, what is this? I mean, whose MSD are you looking at?
Okay, I think that question we can take after this. We can continue that discussion
And the
after that,
second one is you showed like I think two mechanisms. One where in your second when you apply the smaller perturbation,
right?
The peak was shifting towards the left side.
Yes.
Towards the smaller this thing, or whatever this
No, so the
amplitude
thing
was.
is, okay, so you the peak that is encoded because of this 200 cycles gets shifted because of application of this one.
Smaller one, and does it
Smaller one.
asymptotically if you look at even more than 60 what you did?
Right, yes.
It would go to the smaller
It should be going.
whatever
Yeah,
it corresponds
yeah,
to.
yeah.
This. But
That's
again in the next slide you showed you changed the shear rate,
Shear
and
rate,
then
yes.
you showed that there were two peaks appearing.
So the thing is these two, it's not about just the two peaks, but the thing is this here also there is a shift, right? But this shift is happening much faster. For example, the asymptotic limit where you are guessing that the peak should have just moved to the smaller one.
From the last one, I thought the mechanism was like the peak shifts and shift towards the smaller gamma.
Right.
And here it's in this one it
Same
seems
thing,
like
same
there is
thing.
a smaller one appearing, and this one also that grows in size, and this one also.
You are correct. Yeah, that will also
these
grow
are
in size
different
eventually.
or-
No, the same thing. But this effect gets pronounced. So the main effect here is the shifting of the peaks, and that effect is getting pronounced at higher shear rates. So because of the shifting, at some point you will expect them to merge.
In the previous case also you would see that smaller peak
You will
appearing
see,
in the.
you will see the merging, and you will also see the smaller peak gaining more it will gain more strength eventually.
this, yeah, I
but
see,
because
maybe,
yeah. So 60 is not enough to get that effect in this shear rate. Do we have time for one more, or I can take it? Okay, yeah.
Yeah, no, I have just a question that
Yes.
this is a memory. How long you can, I mean, the retention of the memory.
Oh, right.
Yeah,
Okay. So we checked for between 1,000 to 3,000. For our previous paper also we had checked that. It's pretty stable actually. I mean, it will survive for 3,000 is a good enough, 3,000 second is a good enough time. So it will stay for enough time so that we know that this effect is not happening because of that memory going down by itself. Yeah.
Okay, let's thank Sevanti. Further talks can be taken during the lunchtime. Next talk.
Thank you.
Next speaker is Manami Roy.
Thank you everyone to taking time out for attending my talk, and thanks to organizers for this beautiful arrangement and giving me the opportunity to present my work. So today I will be talking about how does gas around the galaxies talk to its surroundings. So let's start. So let's start with cosmic wave. So our universe contains a network of gaseous filament, and within the densest part of this gaseous filament, galaxies form. So in the central part of these galaxies, stars form, and in between stars there are gas which is known as interstellar medium or ISM, and in between galaxies there are gas also which is known as intergalactic medium or IgM. So in between the central part, central star forming optically visible part, and the intergalactic medium, there is another gas, diffuse gaseous halo, which is known as circumgalactic medium, which has a very low density of like less than 10 to the power minus 1 particle per cc, and it has a very complicated temperature structure that I will come to it later. But this gas surrounds the central part of the region, and its size is roughly around virial radius of a galaxy. Now the question is why CGM is important and why do we study CGM? So CGM is habitat for large scale gaseous flows like galactic outflow, galactic inflow, also recycling of gas from the galactic disk to again galactic disk, and then accretion of gas from intergalactic medium and what not. So this large scale gaseous flow helps galaxies to provide fresh and recycled gaseous fuel for star formation and help galaxies to evolve. So to study how galaxy evolve, how galaxy is forming stars, we need to understand circumgalactic medium or CGM in a better way. So this large scale gaseous flow actually structured the CGM in a way. The temperature of the CGM, sorry for the, like it should be for the structure of the slide. So basically it structured the CGM in such a way, it has a wide range of temperature ranging from 10 to the power 4K to 10 to the power 6K. So we roughly divided the temperature of the CGM into 3 phases. One is hot phase, which has roughly a temperature of 10 to the power 6K, and then intermediate temperature of warm phase, which has a temperature 10 to the power 5 to 6K, and then cool phase, which has a temperature 10 to the power 4 to 5K. Now, another important component of the circumgalactic medium, except for the gas, is cosmic rays, which is a charged particle. So cosmic rays are charged particles, so it gets reflected by the galactic magnetic field. So actually we can't trace its origin back. So we have some indirect tracer to trace cosmic rays. One of the tracer is gamma ray. So now let's see how does circumgalactic medium talk to its cosmic rays, but we can't detect cosmic rays, so we will look into the places which shines into gamma rays, which is the indirect tracer for the cosmic rays. So there is a recent observation from our neighboring galaxy Andromeda, and you can see that this is a gamma ray map. This is galactic latitude and galactic longitude. This is our galactic plane, and in the center is the Andromeda center, and around this the circle represent the circumgalactic medium of the Andromeda galaxy. So this left hand side is the observed count, which has all the count, and right hand side is the observed count but saturated one, where we are emphasizing on the low count photon. So you could see a lot of low count photon is coming from the circumgalactic medium of M31 or Andromeda galaxy. So to model this emission, the observers actually model the region around Andromeda into 3 regions. One is the inner region called like inner galaxy, which is roughly around like 5.5 kiloparsec, and then comes 5.5 to 120 kiloparsec spherical halo region, and then outer halo region 120 to 200 kiloparsec. So emission from these 3 regions are modeled and fitted to the overall model, and we can see that we can explain the observed gamma ray emission from the CGM of M31. So now let's see how these gamma rays are actually originated. So we see the gamma ray, and there are multiple possibilities how these gamma rays can form. One of the possible ways to form gamma rays is cosmic rays, and one of the interaction by which this cosmic rays can produce gamma ray is hadronic interaction. So in hadronic interaction, what happens? Yeah, it's not playing.
You have to drive something?
Yes.
So
Say yes, I think. Yes. Will it play?
you have to drive then. Not required later.
Okay.
So what do you do? You have to skip.
Okay, so I'll just say it loud what is in the video. So one cosmic ray proton will basically interact with CGM gas, and it will give rise to neutral pion, which then can decay into gamma rays. And so from cosmic rays we can basically have some gamma rays. So to test this scenario, that whether it can be possible that this amount of gamma rays can be produced from M31 CGM by cosmic rays and by hadronic interaction, we used a simple simulation setup where this is like a Andromeda Mars galaxy setup, and where this central part is galactic disk, which has a temperature of 4 into 10 to the power 4 K with solar metallicity, and around that disk there is galactic halo or CGM, which has a temperature of nearly virial radius 3 into 10 to the power 6 K with 0.1 solar metallicity. So this is our simple galactic setup, and using this setup we consider Andromeda star formation history, and we consider that multiple like supernova explosion in the central region of Andromeda galaxy, where 10% of this energy would be given to cosmic ray in the central part of the galaxy. And also we inject cosmic ray whenever we detect shocks in the galaxy in the circumgalactic medium. So we have two kind of mechanism by which we are accelerating cosmic ray particle or giving energy to cosmic ray particle, one in the central region by star formation and another in the shocks of the outflow. So now using this all coupled equation of thermal and cosmic ray fluid, we actually have a gamma ray map using the hadronic interaction by cosmic rays. So basically, we consider the transport mechanism of cosmic rays to be one, advection from the disk by outflow due to star formation, and then diffusion. And we tried a bunch of models like without diffusion, with different diffusion coefficient. So the best match we got with the observation is with advection and diffusion as a transport mechanism, and with diffusion coefficient, which is 10 to the power 29 centimeter square per second, which explains the observed region around the Andromeda and as well as the flux. So the take home point from this part of my talk is gamma ray observations can be explained by simple cosmic ray physics and cosmic ray accelerated by star formation and in situ shocks in the outflow. Then it can be like cosmic rays can be lifted to the CGM by advection and diffusion. And third, it can do hadronic interaction with CGM protons and give rise to observed gamma rays. Now, in the second part, I will talk about how does this CGM, like a host galaxy CGM, talk to its surrounding satellite galaxy. So, as I mentioned earlier, that CGM has a wide range of temperature starting from 10 to the power 4 to 10 to the power 6 K. So, in cosmological simulation, which is the upper panel, you could see this wide range of temperature distribution with a lot of cold gas like 10 to the power 4 Kelvin gas out there in the CGM. Whereas in the idealized simulation, we don't see that wide range of distribution, and also we don't see cold gas out there in the CGM. So what is happening there, and what is the missing link between cosmological simulation and idealized simulation? So basically, in idealized simulation, we capture these processes, this red color processes like outflow, inflow, recycling of gas, which are inside the galaxy, happening inside the galaxy. Whereas in the cosmological simulation, there are two additional processes by which CGM can get its cold gas. One is by accretion from the intergalactic medium, another is from accretion from the satellite galaxy. In this talk, I will only focus on how satellite galaxy can contribute to the cold gas to the CGM of a host galaxy. So for this, we again use a very simple idealized setup where basically we consider a Milky Way type host galaxy of mass of 2 into 10 to the power 12 solar mass, which has all the components like black hole, stellar bulge, stellar disk, gaseous disk, dark matter halo, and gaseous halo CGM. Whereas for the satellite, we explore different mass distribution from 210 to the power 8 solar mass satellite to 210 to the power 10 solar mass satellite. So satellite has all the components like host galaxy except for the CGM. So I think again the video would be missing. So basically, I just show the video of 2 10 to the power 10 solar mass satellite, 20 10 to the power 9 solar mass satellite, and 200 10 to the power 8 solar mass satellites in this movie. I'll show it later maybe. So let's see what is happening around the satellites and how satellite can contribute to the cold gas to the CGM of a host galaxy. Let's zoom into the satellite region. So this is a zoomed in version around the satellite region, where this is center of the satellite, and this is 6 times scale radius around the satellite. So by triangle I am denoting the satellite gas, and by circle I am denoting the host gas, and blue is the cold gas and red is the hot gas. So basically these are cold satellite gas and these are hot host gas. So first of all, by the process, the satellite can contribute to the cold gas to the CGM of a host galaxy is ram pressure stripping. So when a satellite passes through a CGM of a host galaxy, it suffers a pressure, a drag, and if drag dominates the gravitational pull from the satellite, so basically it will strip the cold gas from the satellite. So this is one obvious process by which satellite can produce cold gas to the CGM. Then there are several other processes like induced cooling. So when a cold gas is getting stripped from the satellite, it tries to get mixed with the hot CGM, and in the mixing layer of this cold gas and hot CGM, there would be significant cooling. So it is known as mixing layer cooling, where satellite gas is trying to mix with the hot CGM gas. So then there can be another induced cooling, which is turbulence driven cooling. So we all know turbulence. So basically when a satellite passing through the CGM of a host galaxy, it can stir the CGM and it can create some local over density region, which can basically drive significant amount of cooling in the host galaxy CGM. Then last but not least important is the even hot host gas falls into the satellite potential and can get cooled from the falling into the potential of the satellite. So these are all the process by which a satellite can contribute significant cooling into the host galaxy CGM and can interact with the host CGM. So this is one snapshot from one of the simulation where 2 10 to the power 10 solar mass satellite is moving around a host CGM in a circular velocity, and you could see there are a lot of cooled stripped gas here. So this is a temperature color bar. So there are a lot of cooled stripped gas behind the satellite galaxy, and on the top of that there are a lot of induced cool gas which are basically coinciding with cool stripped gas. So that means basically most of the induced cooling is happening around this cool stripped gas. That means most of the induced cooling is happening in the mixing layer of this cool stripped gas. Now we can say something quantitatively as well for the stripped cool gas mass. So you could see this is like 3 distribution of satellite I have explored in our work. So one thing is common in these 3 plots. One is like stripped gas mass basically increases over time, then reaches a peak and then decrease. This is true for 3 of the plots. But what is difference? Difference is the massive satellite like 10 to the power 10 solar mass satellite continues to feed cold gas till 4 gigayear, whereas the less massive one like 10 to the power 8 or 9 are getting stripped faster within like 1 to 1.5 gigayear. So the take home message from this part of the talk is, so there is similar amount of induced cooling happening by the satellite as the amount of stripped coal gas from them. We had seen it in the snapshot I had shown. And second is basically most of the induced cooling is contributed by the mixing layer cooling, because we see the induced cool gas are always on the top of the stripped coal gas. And 3, to contribute to the cold gas budget of the host CGM by the satellite significantly and for a significant amount of time like 4 gigayear, we need massive satellite like SMC, LMC like satellites. So yes, thank you.
Questions?
Yeah, it might be a little fundamental. From the first part of the talk, it's like CGM and IGM you have distinguished from the beginning of the slides.
Yes.
I didn't get what is the is there any constitutional difference between CGM and IGM, or you have just because the radius that you marked?
Yeah.
I didn't get why this radius is very significant.
So basically, there is not a very distinct boundary between these two, but basically the diffuse CGM actually in the influence of dark matter halo potential, which is roughly around virial radius of the galaxy. So basically, so that's why we consider it to be a virial radius. CGM is, but whereas IGM is not in the dark matter potential, like influence of dark matter potential. So that's why this boundary of virial radius, but it's not very distinct or it's not very certain also. Like sometimes we consider 2 times virial radius as well. So it's very uncertain parameter as well.
Any other question? If not, let's thank the speaker. Our next speaker is Vaibhav. He will be talking about emergence of transient reverse finger during radial displacement of a shear thickening fluids.
So good afternoon, everyone. So I would like to thank the organizers for giving me this opportunity to present this work in here. So I want to show work that we have done. It is about the transient reverse fingers. So this work explains some kind of instabilities that develop in confined geometries. So to go deeper into it, I'll just try to explain some basics first. So one of them is Safman-Taylor instability. Safman-Taylor instability is, so let's consider you have two fluids of different viscosities and you want to displace one fluid with another, and then you can have two conditions. One is when you can displace a less viscous fluid with a more viscous one, and you can displace a more viscous fluid with a less viscous one. So when in the first case, when you are using more viscous, which is here yellow, to displace the less viscous, then you will see that this circle is growing circle. So that means that any perturbation at the interface, they will get stabilized. But on the other hand, if you displace a more viscous fluid by a less viscous one, then interesting thing happens. So here you can see that all the perturbations they grow, and any perturbations they induce these large scale growth and these repeated tip splitting also. These two are different geometries, which one is the rectilinear and another is the radial, but the phenomena that they shows are same. So the statement is that when a less viscous fluid displaces a more viscous fluid in a porous medium, the interface between the fluid becomes unstable, and you will see the perturbation growth and the large scale structure formation. So since I am talking about the porous medium, so the porous medium is usually opaque. You can't see the flow inside a porous medium with a camera. So in laboratory scale, a Healy-Shaw cell, which is just two glass plates separated by a very thin gap, they are used to study the flow in a porous medium, and it looks like this, that these two are the glass plates, and the gap between them is very smaller than the length of the plates. So here is a top view of this plate, where you can see that there is one inner fluid and there is this outer fluid, and the interface will be unstable if this is more viscous. So why this happens is because you can see here that let's imagine this less viscous fluid is displacing more viscous fluid. Imagine a perturbation that gets developed, and at the locally at the tip of this perturbation, the pressure will be highest, and so is the velocity, because it follows the Darcy's law, and this is why in this situation the perturbation grows. Okay, so why to study these kind of instabilities? So there are two different ways to think about it. One is that these are useful in industrial processes. So the use is that they are not wanted in the industrial processes. One example is the oil recovery process, where what you have is an injector and you have a oil collector. So and here this is the porous field, oil field, where there is oil. And then the water is injected through the injector, and the oil is getting displaced and collected by the producer. But if the water is less viscous than the oil, then these kind of branch fingers will form, And as they form, the displacement efficiency or the oil recovery will be very less, and one would want to reduce this formation of these fingers in such cases. And another example is the carbon sequestration, where if a power plant is producing carbon, it don't want to emit the carbon to the atmosphere. It wants to they want to keep the CO2 at the in underground stored, because so that they don't participate in the global warming. So in this case also, for the efficient storage of those, these fingers are undesirable. Another example where the fingers are desirable is when you have a mixing in at low Reynolds number. So at low Reynolds number, only the diffusion will be there. But if these instabilities are there, they will make new interfaces due to these instabilities, and the mixing can be done at micro scale, micro channels. So the patterns that are formed due to this branching, those patterns are seen everywhere in nature. Some of the examples are the T branches, and this is land topography. This image is taken from the Google Earth, where this near the Uttarakhand and Himachal, these dendrite-like patterns can be seen, and the river branches also. And in human lungs also, you have these air transmitters which forms this branch pattern, as well as lightning also form this branch pattern. So these kind of patterns are seen everywhere. So to study in our system, we are using aqueous cornstarch suspension. So to make a cornstarch suspension, you need the corn flour, water, and you just mix them, and you will see that these polydispersed irregular shaped particle, they will form a non-Newtonian fluid. So this picture is taken by K. Mithindran at SEM department, and this shows the cornstarch particles. So when they are dense enough, when you mix much more amount of those particles in the fluid, then you will see that this behaves like a solid. When you put a sudden impact on the suspension, it behaves like a solid. This is another example which shows that so this is a simulation paper where if the wheel is moving on the surface of the cornstarch suspension, if the rotational speed of the wheel is high enough, it will not sink. But if the rotational speed is low enough, it will sink in the cornstarch suspension. That means if you perturb this cornstarch suspension at high speeds, it will behave more like a solid, and you will feel higher apparent viscosity. So this property, where you feel the higher apparent viscosity with applied stress or the shear strain, is called the shear thickening property. So if you took a cornstarch suspension and put it in a rheometer plate, Sevanti talked about a rheometer plate where you have two plates and you put the sample and you shear it. So if you do rotational test, you can get the viscosity versus shear rate, and you can see that the cornstarch suspension at low shear rate, it acts like a shear thinning fluid, which means that you will feel that its apparent viscosity has been decreased. And then if you increase the shear rate further, you will see that it is now getting more and more difficult for the sample to flow. So the viscosity is increased. But this transition where this shear thickening happens, it highly depends on the concentration of the suspension. If you have the higher concentration of the suspension, then this transition is more drastic than the lower concentration ones. And actually these transitions are also divided into two different parts. Both are shear thickening, but one is continuous shear thickening and other one can be called a discontinuous shear thickening. So to understand this, why this happens, the generally accepted model is that if you have dense particles in the solvent, so most of it is just particle only. So these particles can come into contact with each other when you shear it. So here you can see if you shear the bottom and top plate, these structures will form, and with increasing shear rate or with increasing Peclet number, you will see that this number or the density of these chains are increasing. And as you see increased, then it can also jam itself. So this is like a railway bridge where you have many contacts together, and then it can hold an enormous amount of stresses. So what we will do, we fill this cornstarch suspension in this Haley saw cell, which is just a 2 glass plate, and we will displace this cornstarch suspension with water. So this is a picture where this is outer fluid is the cornstarch suspension, inner is just the water, DI water, which is dyed also, and we'll observe that what happens at the interface. But what we are doing, we are not only observing just the one interface, which I showed you earlier. Here the interface are two. This is the outer interface between the cornstarch and air, and this is the inner interface which is forming when we are injecting water. So it can be seen here that this is a representative picture of the pattern that forms, and you can extract the inner interface as well as this outer interface properties. So let's see what happens when we displace this constant suspension at sufficiently different flow rates. So for low flow rates, what we see is that initially at t equal to 0, we started injecting water. Then as water is going inside, due to the softmental instability, the interface is unstable, and we see multiple tip splitting inside this side and in multiple series of these tip splitting and these integrate patterns formation. And and if we focus at the outer interface, we see that there is nothing interesting going on there. But if we displace the same suspension with the same water, but we change the shear rate or the flow rate, injection flow rate, what we observe is that in addition to the this pattern at the inner boundary, we see that this kind of fingers are also occurring at the intermediate times, and they are very transient in nature. So initially there is nothing, but when the water is injecting, you see that these fingers form, and later time they are gone. So to characterize these interfaces, we calculated the parameter of both the inner and outer interfaces. So we see that the inner interface parameters increase monotonically. These are the Pin. So these increase monotonically, but outer interface parameter shows this non-monotonic behavior because of the enhanced roughness due to the formation of reverse fingers. And one more thing to observe here is that the inner interface growth and outer interface growth, from this picture it looks correlated, because at the time when the slope of the parameter changes, it coincides with the maximum of the outer pattern parameter. And also we see that the number of reverse fingers at these points when the reverse fingers are maximum, the number of reverse fingers with flow rate they increase, but the average separation between them, that is lambda, that doesn't show any change with increasing flow rate. So there are these properties of inner and outer interface. I'll just explain. So inner interface shows multiple tip splitting and formation of these branches. The morphology, which means that this morphology, it is insensitive to the flow rate. They look really same with increasing flow rate. Inner pattern also shows this coalescence event where two fingers can merge with each other, because there is a less amount of surface tension, so it can merge with each other. And parameter increases monotonically, which means that the parameter, because the roughness is always increasing, tip splitting is always happening. On the other hand, at the outer interface, which we see the transient withdrawal of the suspension and the formation of reverse fingers, and the reverse fingers, the formation or the spatial extent of those reverse fingers are also dependent on the flow rate. They also are transient in nature, they fade away at later times, and their temporal variation of the parameter is non-monotonic. So we observe these fingers, and now we want to see that what are the many control parameters. So we started by changing the particle concentration, which means now we are using more dense cornstarch particle. Now there are more number of particles in it, and in this case, and here there are less number of particles, and we see that the reverse fingers are only forming for the denser side of the particle, which is 40 and 42.8% reverse fingers are forming, and for this it is not forming. And also when we change the helicocell gap, which is the gap between two plates, and then we see that the reverse fingers goes away with the increasing gap. So and also, so up to this point, all the patterns are formed when we displace the constant suspension with water. But the another possibility is could the interfacial intention would play any role in the formation of these things. So we see that even if we use the mineral oil, which is an immiscible fluid with respect to the constant suspension, this constant suspension also shows these reverse fingers at the intermediate times. So these reverse fingers are present when you have high shear rates, or when you have high concentration, when you have a low helicocell gap or the higher confinement, and the effect of miscibility, they will form irrespective whether they are displaced by air or water. And there are two characteristics of these reverse fingers that we have identified. One is this: these reverse fingers are not always axially symmetric. So if the reverse fingers are forming only in one way, the inner pattern growth is also connected with that formation, and the inner pattern growth is less in that. So here you can see that R is the inner pattern radius, and NRF is the number of reverse fingers in that segment. So here this is divided into 8 segments. So if the higher the inner pattern radius, and lower the reverse finger. So that means these two are correlated. Other than that, when we change the CS suspension radius, which means that if I am filling the suspension till 5 centimeter in the helicocell or till 10 centimeter, the time when the reverse fingers reach their maximum, it increases monotonically as shown here. And from this time, so that this suggests that there is some information that is transmitting from the inner interface to the outer interface, and that is the stress, and we can calculate the stress propagation velocity from the slope, the inverse of the slope, and that is 4.52 centimeter. These numbers and these scales match closely with the previous study of Maharajan, where they have also studied the stress propagation in constant suspension. So I'll try to finish it quickly. So what we are doing is that we also do some rheology experiments where we want to see what are the regime where our experiments are falling into, and what we see is that shear rates, which these shear rates are calculated from the pattern. So you have the finger growing, you can calculate its velocity, then you can get the shear rates by this formula. And what we see is that the shear rates lie in the shear thickening regime of the constant suspension. And at those regimes, what we see is that the normal stress, which comes when you have which comes positive when you have a frictional contact between particles. So these are positive and these are quite large. So this suggests that at those shear rates, the outer fluid, that is constant suspension, that is forming the frictional force chain networks. So the mechanism that we propose is following: that the the transient stresses are transmitted through the system spanning network of frictional contacts, and then dilation happens, and then at the soft boundary means that at the outer interface the deformation happens, and then the surface tension acts as a restoring force and pushes back. Reverse fingers will then form, and then they will eventually fades away because of the rearrangement of the cornstarch particles. So this was the study. I'd like to just go to the acknowledgement side first. So Professor Ranjini, Palak, and Sayantan have worked with me in this project. I'd like to also thank my lab members for their useful discussions. So this is successful.
Let's thank the speaker. Questions?
So no, can you can calculate this roughness or growth exponent, things like that? And have you tried? I mean, is it known that whether it falls close to this KPZ scaling and KPZ university class and so on?
KPZ scaling I haven't tried. So you are talking about how the inner interface growth. So that I haven't tried. Yeah, but I'm trying it as of now on a different sample. But for this I haven't tried it.
And also, I think you said, but I missed it. Could you say again the cause for the non-monotonic growth for this outer perimeter? Why is it non-monotonic?
Yeah. So as you can see that so the perimeter is just defines the roughness of the interface. So the roughness is maximum when you have reverse fingers. So this is with time. You see that at initial time it is smooth, relatively smooth, and at the intermediate time these fingers form, and later it is all smooth. So the roughness is initially increasing and then decreasing. That's why it is non-monotonic.
Very nice talk. So one thing is you mentioned that how much you fill the suspension, like the constant suspension, that will also affect when you see the reverse fingering. Yes. So what is the smallest limit you have gone to? I mean, is it possible that your like inner and outer fingers will be very close to each other?
Yeah, so we have went to 5 centimeters. So we have filled the constant suspension to a diameter of 10 centimeter minimum.
Okay.
So that is actually enough to see the reverse fingers. But I think if we decrease it further, then we will not.
You won't see the reverse fingers at all.
I don't know. I haven't tried it, but I think it will mix quickly, and then I will not.
Oh, you won't be able to make it out. Okay.
Yeah.
Any other question? Okay, if not, let's thank the speaker. And let's thank all the speakers of this session.